In the grand tapestry of human history, there are stories that echo with the spirit of discovery, tales of brave explorers who ventured into the unknown, across vast oceans and uncharted continents. But of all our journeys, none has been so ambitious, so far-reaching, as the one you are about to hear. This is the story of a modern-day odyssey, not across the seas of Earth, but across the vast, silent ocean of interplanetary space. It is the story of two remarkable emissaries, twin spacecraft named Voyager, launched from our small world to embark on the grandest tour of the cosmos ever conceived. A journey that would carry them past giant, stormy worlds and their myriad moons, and ultimately into the silent, star-strewn darkness between the suns. We'll travel with them from their very conception, born from a fleeting celestial alignment, and follow their lonely path as they became the first human-made objects to ever leave our solar system and touch the void of interstellar space. Their mission has become a timeless epic of human curiosity, ingenuity, and our innate desire to understand our place in the universe. As this story of exploration unfolds, reaching you across the globe, it's amazing to think about where we all are as we share in it. Take a moment to write in the comments where you're listening from and what time it is for you. It would be wonderful to see the vast distances this tale of cosmic travel connects. And to ensure you don't miss out on future stories of great human endeavors, please be sure to subscribe to the channel. Our story begins not in the vacuum of space, but in the minds of a few brilliant scientists and engineers who saw a chance that would not come again for another lifetime. A chance to set sail on the gravitational currents of the heavens. The journey of the Voyager probes did not begin with the fire and thunder of a rocket launch, but in the quiet, methodical world of mathematics and celestial mechanics during the mid-1960s, a time when humanity was just taking its first tentative steps into the cosmic ocean. The Apollo program was in full swing, its sights set on the moon, a destination that, while fantastically ambitious, was still within our celestial backyard. Yet, even as the spotlight shone on the manned missions, a handful of visionaries at places like the Jet Propulsion Laboratory in the sun-drenched foothills of Pasadena, California, were dreaming of a far more audacious voyage. They looked past the moon, past Mars, to the colossal, enigmatic worlds of the outer solar system: Jupiter, Saturn, Uranus, and Neptune. These gas and ice giants, floating in the profound cold and dark so far from the sun, were little more than faint, fuzzy disks in even the most powerful Earth-based telescopes. They held deep secrets about the formation of our solar system, but they were almost incomprehensibly distant. A direct flight to Neptune, the farthest of the quartet, using the rocket technology of the day, was a journey that could take 30 or 40 years. No spacecraft had ever been designed to last that long, to communicate across such a vast abyss, or to navigate a path so complex. The outer planets, it seemed, were destined to remain mysteries for generations to come. But the universe, in its elegant, clockwork precision, was about to offer a shortcut. The solution to this immense problem of time and distance lay in a concept known as the gravity assist, or more colloquially, the planetary slingshot. The theory had been explored in the early days of spaceflight, with a mathematician named Michael Minovich laying the crucial groundwork. But it was still a largely untested idea. In essence, it was a masterful exploitation of orbital mechanics, a game of cosmic billiards where a tiny spacecraft could steal a sliver of a giant planet's immense orbital energy. As a probe approached a planet, the planet's gravity would grab it, pulling it in and accelerating it. The spacecraft would whip around the planet and then fling out the other side, not only with its course altered, but moving at a significantly higher speed relative to the sun. It wasn't just a change of direction. It was a free and colossal boost of momentum, a gift from the planet itself. Using this technique, the long, multi-decade journey to the outer solar system could be dramatically shortened, reduced from a lifetime to a mere dozen years or so. But there was a catch, and it was a significant one. To tour the outer planets efficiently, to hop from one world to the next using these gravitational slingshots, the planets themselves had to be in just the right positions in their orbits. They needed to be aligned in a specific way, like beads on a string, so a spacecraft could fly from Jupiter to Saturn, use Saturn's gravity to aim for Uranus, and Uranus's to aim for Neptune. Such an alignment was extraordinarily rare. In the summer of 1965, a young aerospace engineering graduate student named Gary Flandreau was working a temporary job at the Jet Propulsion Laboratory. He was tasked with a seemingly mundane project to study and calculate potential long-distance trajectories for future missions, to find efficient paths through the solar system. He spent his days poring over complex orbital data, charting the slow, grand waltz of the planets. He plotted their positions forward in time into the 1970s and 1980s, and it was then that he noticed it. Staring back at him from his charts and printouts was the key. He saw that beginning in the late 1970s, Jupiter, Saturn, Uranus, and Neptune would enter a rare alignment, an arrangement that occurred only once every 175 years. Flandreau realized the profound implication of his discovery. This was the window. This was the one chance in a lifetime, indeed, one chance in 3 lifetimes, to make the journey a reality. A single spacecraft could be launched toward Jupiter, and then, with a series of perfectly executed gravity assists, it could perform a grand tour of all 4 outer planets, completing in about 12 years what would otherwise take 30. The opportunity was breathtaking, a celestial invitation that could not be ignored. Flandreau's calculations and the grand tour concept ignited a fire of excitement within NASA and the broader scientific community. The idea was magnificent in its scope. The plan that began to take shape was even more ambitious than a single spacecraft. The original vision called for 2 separate missions, each with 2 probes. One pair would be launched in 1977 to visit Jupiter, Saturn, and Pluto. The other pair would launch 2 years later, in 1979, and fly by Jupiter, Uranus, and Neptune. These thermoelectric outer planets spacecraft, or TOPS, were to be marvels of engineering, designed to last for a decade or more, pushing the boundaries of what was technologically possible. The missions would fundamentally rewrite our textbooks, transforming our understanding of the solar system from a collection of 9 points of light into a family of unique and complex worlds. The scientific payoff would be incalculable. However, the dream of the grand tour soon collided with the harsh realities of politics and economics. The early 1970s were a difficult time for NASA. The triumphant glow of the Apollo moon landings was fading, and with the Vietnam War and domestic issues consuming the national budget, the agency's funding was being slashed dramatically. In this climate of austerity, the grand tour, with a projected cost of $1 billion, the equivalent of over $6 billion today, was seen by many in Washington as an unjustifiable extravagance. A mission to the distant, cold, and seemingly barren outer planets felt like a luxury compared to more pressing concerns on Earth. The project was canceled in 1972, and the rare celestial window that Gary Flandreau had discovered seemed destined to close, the opportunity lost for another 175 years. But the dream was too powerful to die completely. The scientists and engineers at JPL, refusing to give up, went back to the drawing board. They proposed a scaled-down, more focused, and, crucially, much cheaper mission. Instead of 4 spacecraft, there would be 2. Instead of targeting all the outer planets, the mission would officially be limited to Jupiter and Saturn. This new, more modest proposal was called the Mariner Jupiter-Saturn mission. By framing it as an extension of the successful and relatively low-cost Mariner program that had already explored Venus and Mars. They made it more palatable to the budget-conscious decision-makers. The cost was brought down to a quarter of the original estimate, about $250 million. This time, the plan was approved. Though it was a compromise, a shadow of the original grand tour, it was a lifeline. Within the halls of JPL, however, a quiet act of inspired foresight took place. While the official mission was only to Jupiter and Saturn, the engineers building the two probes did so with the grand tour still secretly in their hearts. They knew that if the Jupiter and Saturn encounters were successful, and if the spacecraft were still healthy, the possibility of extending the mission to Uranus and Neptune might re-emerge. So they built the spacecraft to last. They over-engineered them, giving them redundant systems and robust components capable of withstanding a much longer and more arduous journey than the official plan called for. They carefully calculated a trajectory for the second of the two probes that, after its encounter with Saturn, would keep the option of a flight to Uranus and Neptune open. It was a gamble, an act of faith in their own craftsmanship, and a hope that the future would be kind. The mission, later renamed in a public competition to the more evocative Voyager, was officially born. The dream of the grand tour was alive, tucked away within the circuits and structure of two unassuming machines, waiting for its chance to be fulfilled. The celestial alignment was drawing closer. The clock was ticking, and the monumental task of forging these messengers to the stars could now begin. With the mission greenlit and a celestial deadline looming, the engineers and scientists at the Jet Propulsion Laboratory embarked on one of the most ambitious construction projects in human history. They were not merely building machines. They were forging autonomous explorers, crafting extensions of human curiosity that had to survive for years and potentially decades in an environment more hostile than anything on Earth. Every circuit, every weld, every line of code had to be perfect. There would be no second chances, no roadside assistance on the long, dark highway to the stars. The two spacecraft, identical twins named Voyager 1 and Voyager 2, were masterpieces of functional design, their forms dictated by the immense challenges they would face. Each one was a complex, somewhat gangly-looking assembly of instruments, booms, and antennas, weighing close to 815 kilograms, or nearly 1,800 pounds, roughly the size of a small car, though with a far more intricate purpose. The core of each Voyager was a 10-sided, ring-like structure known as the bus, about 1.5 meters or 6 feet across. This bus was the spacecraft's torso, housing the delicate electronic brains, the command and data systems, and the attitude controls. It was a marvel of packaging, with compartments filled with the most advanced, radiation-hardened electronics of the 1970s, all designed to withstand the violent shaking of launch and the profound, unending cold of deep space, where temperatures would plummet to hundreds of degrees below freezing. Perhaps the most critical challenge was providing the spacecraft with a continuous and reliable source of power. For missions exploring Mars or Venus, large solar panels could be used to drink in the abundant sunlight. But the Voyagers were bound for the dim outer reaches of the solar system, where the sun shrinks to a brilliant but distant star. At Jupiter, sunlight is only 4% as strong as it is at Earth. By the time a probe reached Neptune, that light would be 1,000 times fainter. Solar power was simply not an option. The solution was a form of nuclear energy, a steady, reliable heartbeat for the long voyage. Each spacecraft was equipped with 3 radioisotope thermoelectric generators, or RTGs, mounted on a boom extending away from the main body. These were not nuclear reactors in the conventional sense. They had no moving parts and performed their magic through a simple, elegant process. At the core of each RTG was a small ceramic pellet of plutonium-238, a man-made radioactive element. As the plutonium naturally decayed, it released a steady, predictable flow of heat. This heat was captured by a web of special metallic junctions called thermocouples, which, when heated, generate a small electric current. It was a solid-state power plant, turning the slow, inexorable decay of atoms directly into the electricity needed to run the computers, power the radio, and operate the scientific instruments. At the beginning of the mission, the RTGs provided about 470 watts of power, enough to light up a few household light bulbs. It was a modest amount of energy, but it was constant, and it would last for a very long time. The engineers knew that the power output would slowly decrease as the plutonium decayed, a fact that would, decades later, force the mission controllers on Earth to make agonizing decisions about which of the aging probe's instruments to turn off forever. With a source of power secured, the next great challenge was communication. How could these tiny emissaries whisper their secrets back to Earth across billions of kilometers of empty space? The answer was the most prominent feature of the spacecraft, a massive, gleaming white high-gain antenna, a parabolic dish 3 7/10 meters, or 12 feet, in diameter. This dish had to be pointed toward Earth with pinpoint accuracy at all times, a task managed by the spacecraft's attitude control system. which used a combination of tiny thruster firings and a special star tracker locked onto the sun and the bright star Canopus as celestial guideposts. When the Voyagers transmitted their data from the outer planets, the signal that finally reached the giant radio telescopes of the Deep Space Network on Earth was astoundingly faint. Its power was less than a billionth of a watt, a whisper of energy so infinitesimal that it is dwarfed by the energy of a single falling snowflake. To pull this coherent message from the background hiss of the cosmos was a technological miracle in itself, a testament to the sensitivity of the receivers on Earth and the power of the transmitter aboard the spacecraft. The mind of each Voyager was a trio of interconnected computer systems, primitive by today's standards, yet remarkably robust and effective for their time. The main brain was the Computer Command System, or CCS. In an age where a simple smartphone can store terabytes of data, the total memory of the Voyager's main computer was a mere 69 kilobytes. It was just enough to hold the complex sequences of commands for planetary flybys, manage the collection and transmission of data, and monitor the health of the spacecraft's systems. The flight software was a work of art, an intricate digital ballet designed to make the most of this limited memory. Because of the vast distances involved, the Voyagers had to be highly autonomous. Direct, real-time control from Earth was impossible due to the speed of light. A radio signal traveling from Earth to Saturn could take over an hour and a half to arrive. A command to take a picture would not reach the spacecraft for 90 minutes, and the picture itself would take another 90 minutes to travel back. This round-trip time of over 3 hours made joysticking the spacecraft impossible. It had to know what to do on its own. The mission controllers on Earth would painstakingly assemble and test long sequences of commands, bundle them into a message, and beam it out to the spacecraft days in advance of a critical maneuver or observation. The Voyager would then store these commands and execute them flawlessly at the appointed time. A faithful robotic servant carrying out its duties in the profound solitude of deep space. To safeguard against failure, the computer systems were fully redundant. There were 2 of everything: 2 command computers, 2 flight data systems, 2 attitude control computers. If one failed, the other could take over, a design philosophy that would prove critical to the mission's longevity. But the true purpose of the Voyagers, the very reason for their existence, was to carry a suite of advanced scientific instruments, the senses through which humanity would experience the outer planets for the first time. To ensure these sensitive instruments could take clean measurements, many were mounted on booms that extended from the central bus. A 10-meter or 33-foot boom held the television cameras and other instruments that needed to be pointed, while a much longer 13-meter or 43-foot boom, which unfurled in space like a firecracker snake, carried the delicate magnetometers. This placed them far away from the faint magnetic fields generated by the spacecraft's own electronics, ensuring they could accurately measure the colossal magnetic environments of the gas giants. The eyes of the mission were the cameras of the imaging science system. There was a narrow-angle camera for detailed close-up shots, and a wide-angle camera for broader, contextual views. These were not digital cameras in the modern sense. They used a technology called a Vidicon tube, a type of television camera that stored an image on a photosensitive plate that was then scanned by an electron beam to be converted into a digital signal. Other instruments acted as the probe's other senses. Infrared and ultraviolet spectrometers analyzed the chemical composition of atmospheres, rings, and moons, acting as a sense of taste and smell. A suite of detectors for cosmic rays, low-energy charged particles, and plasma waves served as a sense of touch, feeling the invisible particles and fields that dominate the interplanetary environment. Together, this array of 11 instruments would work in concert to paint a complete picture of these new worlds, a picture far more detailed and dynamic than humanity had ever dared to imagine. Assembling these technological marvels was a process of painstaking precision. In the cavernous, sterile, clean rooms at JPL, technicians in white suits and masks, looking like surgeons, worked meticulously to put the pieces together. Every component was tested, retested, and subjected to conditions far harsher than it was ever expected to face. The completed spacecraft were placed on shake tables to simulate the violent vibrations of a Titan Centaur rocket launch. They were baked in giant thermal vacuum chambers to ensure they could withstand the extreme temperature swings between direct sunlight and deep space shadow. This grueling process was designed to weed out any potential flaw, any weakness that could jeopardize the mission millions of miles from home. The strategy of building two identical spacecraft was a core part of the mission's philosophy. It provided critical redundancy. If one failed, the other could still carry on. It also allowed for different trajectories. Voyager 1 was placed on a faster, more direct path to Jupiter and Saturn, one that would ultimately fling it out of the solar system in a northerly direction. Voyager 2 was launched first, but placed on a slightly slower, more curved trajectory. This was the path that preserved Gary Flandreau's original dream. It was the path that, if all went well, would allow it to use Saturn's gravity to bend its course toward Uranus, and then Uranus's gravity to aim for Neptune, a cosmic bank shot of unimaginable scale and complexity. After years of design, construction, and relentless testing, the two Voyagers stood ready. They were more than just machines of metal and wire. They were the embodiment of a generation's scientific ambition, forged in the fires of human ingenuity and poised on the edge of the launch pad, ready to begin the greatest voyage of discovery ever undertaken. While the engineers were forging the physical bodies of the Voyager probes, a small, dedicated team was working on a different but equally profound challenge: forging their souls. For these spacecraft were to be more than just robotic scientists on a mission of data collection. They were to be ambassadors, emissaries from the shores of our world to the vast, unknown ocean of the cosmos. Tucked away on the side of each probe, sheltered from the harsh radiation of space by a protective aluminum cover, was a message. It was a greeting card from humanity, a time capsule of our world, a single, hopeful gesture cast into the void. This message took the form of a golden phonograph record, a name that evoked both its preciousness and its humble, old-fashioned technology. It was a story of who we are, what we feel, what we create, and where we live, encoded in sound and images, and sent on a journey that would last for eons. The driving force behind this extraordinary project was the astronomer Carl Sagan, a brilliant scientist at Cornell University who possessed the rare gift of a poet's heart. Sagan was a man captivated by the grand scale of the universe and haunted by the profound question of whether humanity was alone within its silent, sprawling immensity. He had been instrumental in placing a similar, though far simpler, message, a small engraved plaque, aboard the Pioneer 10 and 11 spacecraft a few years earlier. But for Voyager, he envisioned something far richer, more detailed, and more emotional. He saw a chance to send not just a diagram, but a symphony. He assembled a small, passionate committee of thinkers, artists, and scientists who were given an almost impossibly short deadline, a mere 6 weeks, to curate a message that could represent the entirety of our planet. The creative director was Anne Druyan, a writer and producer who would later become Sagan's wife. The technical director was Frank Drake, a pioneer in the search for extraterrestrial intelligence. The design director was the artist John Lumberg, and the whole project was produced by science writer Timothy Ferris. Together, they embarked on a frantic, exhilarating quest to distill the essence of human experience onto a single object. The medium they chose was a phonograph record, a disc 30 centimeters or 12 inches in diameter, made of copper and plated in a shimmering layer of pure gold to protect it from the corrosive effects of space dust over billions of years. A record was chosen for its simplicity. Unlike a modern digital disc, which requires complex computers to read, a phonograph record can be understood through basic physics. It is a physical artifact, its grooves a tangible landscape of sound. The committee imagined a distant, advanced civilization stumbling upon the silent Voyager. They might not understand the spacecraft's electronics, but they could, perhaps, decipher the simple, mechanical nature of the record. To help them, the record's protective aluminum cover was etched with a set of diagrams, a kind of instruction manual for any potential finders. At the heart of these instructions was a brilliant cosmic map designed by Frank Drake. It showed the location of our sun relative to 14 pulsars, which are rapidly spinning neutron stars that emit beams of radiation like celestial lighthouses. Because the pulse rate of each pulsar is unique and slows down at a very precise, predictable rate, this map doesn't just show where we are, but also when the record was made. It's a return address and a timestamp written in the language of astrophysics. Other diagrams showed the hydrogen atom in its two lowest states, a fundamental transition in physics that provides a universal unit of time, about 1/10,000,000,000th of a second, which could be used to understand the other diagrams, including the one that showed exactly how to play the record. The correct rotational speed, 16 2/3 revolutions per minute, was given in this universal unit, along with a simple drawing of the record and the stylus needed to play it. With the instructions complete, the team faced the monumental task of deciding what to put in the grooves themselves. The record was divided into 4 main sections: greetings in many of the world's languages, a collage of sounds from Earth, a selection of music from various cultures and eras, and a collection of encoded images. The greetings were a chorus of welcome from across the globe. The team worked with the United Nations to collect brief salutations in 55 different languages, from the ancient Akkadian spoken in Sumer 4,000 years ago to modern dialects like Mandarin Chinese and Welsh. Each speaker was asked to give a simple, friendly message. The UN Secretary General at the time, Kurt Waldheim, recorded a hopeful sentiment, and a touching, simple greeting was added from Sagan's own 6-year-old son, Nick, who said, "Hello, from the children of planet Earth." This linguistic tapestry was meant to convey the diversity of human culture, a planet of many voices speaking as one. Next came the sounds of Earth, an intricate, 12-minute-long audio essay conceived and produced by Anne Druyan. It was designed to tell the story of our planet through sound alone. It begins with the fundamental sounds of geology and biology, volcanoes, earthquakes, and wind, followed by the cries of chimpanzees and the songs of wild dogs. It progresses to the sounds of human technology, from the clanging of a blacksmith's hammer to the roar of a Saturn V rocket, the very kind that would launch the Voyagers themselves. But woven throughout are the deeply personal, intimate sounds of human life, the rhythmic beat of a human heart, a mother's first words to her newborn child, the sound of a kiss. In one of the most moving parts of the project, Druyan, who was falling in love with Sagan during these intense weeks of work, wanted to include the sound of a human mind. She had her own brainwaves recorded by a doctor while she meditated on a series of thoughts, including the history of ideas, the plight of civilizations, and what it was like to fall in love. That 1-minute recording of her thoughts, translated into sound, is on the record, a silent, personal message of love and wonder drifting through the cosmos. Perhaps the most debated and emotionally charged part of the record was the 90 minutes of music. The team aimed for a selection that was both artistically magnificent and culturally diverse, a global mixtape for the stars. The music began with the soaring, mathematical beauty of Johann Sebastian Bach's Brandenburg Concerto, chosen to represent the order and harmony humanity was capable of achieving. This was followed by music from around the world, the thunderous percussion of Senegal, the delicate melodies of a Peruvian panpipe, the intricate rhythms of Javanese gamelan music from Indonesia, and the haunting song of a lone Navajo singer. The Western classical tradition was represented by giants like Mozart and Beethoven, but so too was American popular music. The team included Louis Armstrong's soulful, melancholy blues to capture the sound of jazz, and in a bold move, they added Chuck Berry's 1958 rock and roll anthem, Johnny B. Good. Sagan championed this choice, arguing that rock music was one of America's most powerful cultural exports, a symbol of youthful hope and restless energy. The Beatles' song, Here Comes the Sun, was also selected, and the band enthusiastically approved, but their record label, EMI, refused to grant the rights, a small, bureaucratic hurdle that stood in the way of a message to the cosmos. Finally, the record contained a gallery of 116 images, which were encoded as audio signals that could be reconstructed, line by line, into a picture. The visual story began with the basics, a circle, a square, and definitions of our mathematical and chemical principles. It then zoomed out, showing our place in the cosmos with images of the sun, the planets, and our home, the Earth, as seen from space. From there, the focus narrowed, diving into the fabric of life on our world. There were diagrams of DNA, human anatomy, and scenes of conception and birth. The images showcased the diversity of our species and our cultures. A man from Guatemala, a woman scientist with a microscope, a group of school children of different ethnicities, an elder of the San people of Botswana. The gallery depicted how we live: a family eating dinner, a supermarket aisle overflowing with food, a photograph of a traffic jam in an Indian city to show our problems as well as our triumphs, and stunning architectural achievements like the Taj Mahal and the Sydney Opera House. It was an honest, unvarnished portrait, a celebration of our accomplishments and an acknowledgement of our flaws, all sent with the hope that some distant intelligence might one day see it and understand something of who we were. In the end, the golden record was as much a message to ourselves as it was to the stars. The chances of it ever being found by an alien civilization are infinitesimally small. The Voyagers will drift for tens of thousands of years before they even come remotely close to another star. But the act of creating the record was a profound one. It forced a small group of people to think deeply about what it means to be human, to look at our world with the eyes of an outsider and ask, what is worth saving? What is worth remembering? The golden record is a testament to human hope, a quiet, golden whisper sent into the vast cosmic silence, carrying the music, the voices, and the dreams of a small blue world. After their spectacular departure from Earth in the late summer of 1977, the twin Voyager spacecraft settled into the long, quiet cruise phase of their journey. For more than a year and a half, they sliced through the black, silent emptiness of the inner solar system, their world a predictable routine of system checks and course corrections. On Earth, their human controllers watched and waited, their patience a necessary virtue in the slow and deliberate world of interplanetary travel. The Voyagers were crossing the vast, empty expanse of the asteroid belt, a region far less crowded than popular fiction would suggest, but still a zone of potential hazard. They emerged unscathed, their trajectories perfect, their instruments dormant but healthy. And then their destination began to grow. The celestial king, Jupiter, began its slow transformation from a brilliant, star-like point of light into a true destination, a world that swelled in the camera's viewfinders day by day. On the television screens at the Jet Propulsion Laboratory, A fuzzy, indistinct marble of faint beige and white began to resolve itself into a place of staggering complexity and violent beauty. The anticipation was electric. This was the moment the mission was designed for, the first test of its promise. In March of 1979, Voyager 1 made its grand arrival. It was not a landing, not a slow insertion into orbit, but a screaming, high-speed flyby, a fleeting encounter that had been choreographed for years. As it plunged toward the giant planet, its instruments came alive, and a torrent of data, the likes of which had never been seen before, began to stream back across the 650 million kilometers, or 400 million miles, to a rapt audience on Earth. The images that filled the monitors were breathtaking, a cosmic masterpiece of abstract art painted on a canvas of unimaginable scale. Jupiter was a churning, chaotic ball of gas more than 11 times the diameter of Earth. A world so vast it could hold all the other planets in the solar system within its volume. Its atmosphere was a tapestry of vibrant colors: creams, rust reds, oranges, and browns, all stretched into magnificent parallel bands that encircled the globe. These were colossal jet streams, winds whipping around the planet at speeds exceeding 400 kilometers per hour, or 250 miles per hour. The lighter-colored bands, called zones, were plumes of rising, cooling ammonia ice, while the darker belts were regions of warmer, sinking gas. The entire atmosphere was a violent, perpetual ballet of chemical storms, a deep and turbulent ocean of hydrogen and helium. And there, in its southern hemisphere, was the planet's most famous and enigmatic feature: the Great Red Spot. For 3 centuries, astronomers on Earth had seen it as a faint, ruddy blemish, a permanent-seeming feature on a restless world. Voyager 1 revealed it for what it truly was: a colossal anticyclone, a hurricane of such titanic proportions that it could swallow the entire planet Earth 2 or 3 times over. It was a storm that had been raging for at least 300 years, a swirling crimson eye in the Jovian sky, locked between 2 powerful jet streams. The probe's cameras captured movies of its dynamic motion, showing smaller storms being consumed by its gargantuan vortex, a display of meteorological power that dwarfed anything in human experience. But Jupiter's spectacle was more than just skin deep. As Voyager 1 swung behind the planet, it detected the unmistakable signature of immense lightning bolts flashing within the deep cloud decks, discharges of electricity thousands of times more powerful than any terrestrial thunderstorm. It also discovered a faint, shimmering aurora, a ghostly glow dancing over the planet's poles, a sign that Jupiter possessed an immense and powerful magnetic field. This magnetosphere was the largest single structure in the solar system, a teardrop-shaped bubble of intense radiation so vast that if it were visible from Earth, it would appear larger in our night sky than the full moon. The probe had to weather a storm not just of wind, but of radiation, a tempest of charged particles trapped by the magnetic field that were 1,000,000 times more intense than the lethal Van Allen belts surrounding Earth. The engineers' foresight in radiation hardening the spacecraft's electronics had paid off. The probe survived its baptism by fire. During the flyby, the mission team decided to take a long exposure photograph, looking back toward the planet's dark side, a shot designed to specifically search for any faint, undiscovered moons. When the image came back, they found something even more surprising: a thin, ethereal ring. Unlike Saturn's bright, majestic hoops of ice, Jupiter's ring was a tenuous, dusty thing, almost invisible. It was the first time a planetary ring had been found by a spacecraft, and it was a revelation. It proved that these beautiful structures were not unique to Saturn, but perhaps a common feature of the giant planets. The discovery was a subtle grace note in the midst of the planet's overwhelming power. Yet, for all the wonders of Jupiter itself, the most revolutionary discoveries were still to come. After its closest approach to the gas giant, Voyager 1's trajectory carried it on a tour of Jupiter's 4 largest moons, the Quartet of Worlds, first spotted by Galileo Galilei in 1610, which had earned them the name the Galilean moons. For centuries, they had been mere points of light. Now, they were about to resolve into unique, individual worlds, each one more shocking than the last. First came Io. Scientists had expected to see a cold, dead, crater-pocked world like our own moon. Instead, the images revealed something utterly bizarre, a world painted in garish shades of yellow, red, orange, and black, with a surface almost completely devoid of impact craters. It looked, as one scientist famously quipped, like a celestial pizza. The lack of craters suggested a very young, constantly renewed surface, but the reason why defied all expectations. The answer came from a sharp-eyed navigation engineer at JPL named Linda Morabito. Her job was to analyze long-exposure images of the moons against the background stars to refine the spacecraft's trajectory. While examining an image of Io, she noticed a strange, faint smudge clinging to the moon's bright limb. At first, she dismissed it as an imaging artifact, perhaps a ghost image of a brighter star. But it persisted in other images. When she enhanced the contrast, the smudge resolved into an unmistakable shape, a vast, umbrella-shaped plume. an explosion rising from the surface and silhouetted against the black of space. Morabito had discovered a volcano. And not just one. Voyager 1 would go on to spot 8 more active volcanic eruptions during its brief flyby. Io was, without a doubt, the most volcanically active body in the entire solar system. Plumes of sulfur and sulfur dioxide were blasting material up to 300 kilometers, or nearly 200 miles, into the sky, creating a thin, noxious atmosphere and coating the surface in its vibrant, colorful deposits. The cause of this internal fire was Jupiter itself. The moon is locked in a gravitational tug-of-war with the giant planet and its neighboring moons, a constant squeezing and stretching that generates immense friction deep within Io's core, heating it to a molten state. The discovery was a paradigm shift, overturning the cold, dead moon theory and revealing that worlds could be shaped by powerful forces other than just impacts and ancient heat. Next in line was Europa, and it presented a mystery as profound as Io's fire. Where Io was a world of chaotic color, Europa was a sphere of pale, serene white, as smooth as a billiard ball. Its icy surface was covered in a complex network of dark, reddish-brown lines and cracks, crisscrossing each other like a frantic scribble on a canvas. Some stretched for thousands of kilometers or miles across the surface. But like Io, Europa was strangely devoid of craters. This again pointed to a young, active surface, but one shaped by very different processes. The smooth ice and the vast network of fractures led scientists to a tantalizing and world-changing hypothesis. Beneath its frozen crust, which might be several kilometers or miles thick, lay a vast, globe-spanning ocean of liquid salt water, kept from freezing by the same tidal forces that melted Io's interior. The lines on the surface were likely cracks in the ice, where warmer, darker water from below had welled up and refrozen. The implications were staggering. On Earth, wherever we find liquid water, we find life. Suddenly, this small, distant moon of Jupiter became one of the most compelling places in the solar system to search for extraterrestrial life. The tour continued past the 2 largest moons, Ganymede and Callisto. Ganymede, the largest moon in the solar system and bigger than the planet Mercury, revealed a complex and ancient world with 2 distinct types of terrain: old, dark, heavily cratered regions, and younger, lighter areas marked by long, parallel grooves and ridges, suggesting a history of tectonic activity. Callisto, by contrast, was a portrait of antiquity, its surface a dark, battered landscape so saturated with craters that it seemed almost no new impacts could occur without erasing an old one. Its face was a record of 4.5 billion years of bombardment. 4 months later, in July 1979, Voyager 2 arrived to perform its own symphony. It followed a slightly different path, allowing it to take a closer look at Europa and to see how the dynamic Jovian system had changed. It saw that Io's volcanic plumes were still erupting, some having ceased while new ones had appeared, confirming the moon's relentless activity. With its primary mission at Jupiter now complete, each spacecraft prepared for the next leg of its journey. Using the immense gravity of the king of planets, they performed the slingshot maneuver that had been the dream of the mission's planners. As they whipped around Jupiter, they were flung forward with a tremendous burst of speed, their trajectories bent perfectly toward their next target, the ringed wonder of the solar system, Saturn. The Jovian symphony was over, but its echoes had forever changed our understanding of how worlds are born and how they live. The solar system was proving to be a far stranger, more dynamic, and more wonderful place than anyone had ever imagined. After the thunderous crescendo of the Jupiter encounter, a new kind of quiet descended upon the Voyager mission. The two probes, now flung forward with the immense momentum gifted to them by the gas giant, sailed onward into the deepening twilight of the solar system. For nearly 2 years, they traveled the vast, empty gulf between the two largest planets, a journey of more than 600 million kilometers, or close to 400 million miles. On Earth, the data from Jupiter was still being analyzed, a treasure trove of discovery that was rewriting textbooks. But all eyes at JPL were now looking ahead. The next destination was the jewel of the solar system, the planet that had captivated human imagination for centuries with its ethereal and majestic rings. Saturn. It was a world that promised a different kind of beauty, less chaotic and violent than Jupiter, more serene and ordered. But as the Voyagers would soon reveal, this placid beauty masked a system of staggering and often baffling complexity. In November of 1980, Voyager 1 made its appointment with the ringed world. From a distance, Saturn appeared as a pale, butterscotch-colored globe, more subdued than Jupiter, its atmospheric bands less distinct, and its colors more muted. This was due to a high-altitude haze that veiled the deeper, more turbulent cloud decks. Yet this serene facade still held immense power. The winds on Saturn were even more ferocious than on Jupiter, screaming around the equator at speeds that reached 1,800 kilometers, or 1,100 miles, per hour, some of the fastest in the entire solar system. But the main attraction, the feature that had drawn the gaze of astronomers since Galileo first sketched them as strange handles, was the rings. From Earth, even through the best telescopes, they appeared as a set of 3 or 4 broad, solid-looking bands, the A, B, and C rings, separated by dark gaps, most famously the Cassini division. Scientists expected Voyager 1 to provide a clearer, more detailed picture of this known structure. What they received instead was a revelation that shattered all their preconceived notions. As the probe drew closer, the images it sent back showed that the broad, seemingly solid rings dissolved into an intricate and breathtaking tapestry of thousands upon thousands of individual ringlets, packed together like the grooves on a phonograph record. Where astronomers had expected a handful of divisions, Voyager saw a nested, almost infinite set of structures. The rings were not a static, solid sheet of material, but a dynamic, shimmering river of countless ice particles, ranging in size from tiny dust grains to chunks as large as a house, each in its own perfect orbit around the planet. The sheer complexity was dumbfounding. But within this intricate system, Voyager discovered features that seemed to defy the known laws of physics. In the B ring, the cameras captured strange, dark, radial features that stretched across the ringlets like the spokes on a bicycle wheel. These spokes would form and dissipate over the course of a few hours, rotating around the planet not at the speed of the orbiting ice particles, but at the same rate as Saturn's own magnetic field. The sight was mystifying. They seemed to violate the sacred rules of orbital mechanics. The leading theory was that tiny, dust-sized particles were being levitated out of the main ring plane by electrostatic forces, like static cling on a cosmic scale, and were then being swept along by the planet's powerful magnetosphere. It was a glimpse into a set of physical processes that no one had anticipated. Even more bizarre was the behavior of the F ring, a thin, faint strand of material that lay just outside the main rings. Voyager 1's close-up images showed that this single, narrow ring was actually composed of multiple strands that were strangely kinked, knotted, and even braided around each other. This was orbital chaos, a structure that should not have been stable. The explanation came in the form of 2 tiny, newly discovered moons, which were immediately christened Prometheus and Pandora. These 2 small moons orbited just inside and just outside the F ring, and their gravitational influence acted to confine the ring particles between them. They were cosmic shepherds, tirelessly herding the straying flock of ice particles and, in the process, twisting them into their bizarre, braided pattern. The discovery of these shepherd moons was a major breakthrough, explaining how such narrow and delicate ring structures could exist at all. Beyond the rings, Voyager 1 turned its attention to Saturn's diverse family of moons. Most were small, icy worlds, battered by billions of years of impacts. There was Mimas, a moon dominated by a single colossal impact crater, Herschel, so large that it gave the moon an uncanny resemblance to the Death Star from the movie Star Wars. There was Enceladus, a world so bright and white that it reflected nearly 100% of the sunlight that struck it, making it one of the most reflective objects in the solar system. Its surface was unnervingly smooth in places, hinting at some kind of recent geological activity that had paved over older craters. A tantalizing clue that would only be fully understood decades later by the Cassini mission. And there was the two-toned Iapetus, half of which is as bright as snow, and the other half as dark as coal, a celestial yin and yang. But the prime target of Voyager 1's Saturn encounter, the destination for which it would sacrifice the rest of its planetary tour, was Titan. Titan was an object of immense scientific desire. It was the second largest moon in the solar system, larger than the planet Mercury, and crucially, it was the only moon known to possess a substantial atmosphere. For years, scientists had dreamed of what might lie beneath its thick, orange haze. Was there a surface with oceans, continents, and perhaps even some form of life? To find out, the mission planners designed a special trajectory for Voyager 1. The probe would dive down, passing close behind Titan, a maneuver that would allow its radio signal to pass through the moon's atmosphere on its way to Earth, giving scientists a detailed profile of its composition, pressure, and temperature. But this trajectory came at a great cost. The powerful gravity of Titan would bend Voyager 1's path sharply, flinging it up and out of the ecliptic plane, the flat disk where all the planets orbit. This maneuver would make it impossible for Voyager 1 to continue on to Uranus and Neptune. It was a one-way trip. The choice was made. The guaranteed, groundbreaking science at Titan was worth sacrificing the rest of the grand tour for this one probe. As Voyager 1 made its close approach, the world held its breath. The data streamed in, revealing an atmosphere even thicker and more complex than imagined. It was denser than Earth's, with a surface pressure about 1.5 times that of our own planet. Its composition was overwhelmingly nitrogen, just like Earth's, but with a significant fraction of methane and other organic compounds. The temperature at the surface was a frigid -179 degrees Celsius, which is about -290 degrees Fahrenheit, a temperature at which methane could exist as a liquid a gas or a solid, much like water does on Earth. The probe had found tantalizing evidence for a methane cycle, with methane clouds, methane rain, and perhaps even methane rivers and oceans. But when the cameras tried to peer through the haze, they saw nothing. The atmosphere was completely opaque, a uniform, featureless orange smog that shrouded the surface in total mystery. There was a sense of disappointment, of being denied the ultimate prize. Yet, the chemical discoveries were profound, painting a picture of a world that was a kind of prebiotic Earth held in a deep freeze, a planetary-scale laboratory for the kind of organic chemistry that may have led to life on our own planet. With its primary mission complete, Voyager 1 cast one last look back at the magnificent Saturn system, and then, as planned, began its long, lonely climb out of the solar system, its planetary adventures now over. 9 months later, in August of 1981, it was Voyager 2's turn. Its arrival was met with a moment of heart-stopping drama. As the spacecraft approached, the scan platform, the movable turret upon which the cameras and other pointed instruments were mounted, suddenly seized up. The platform had been moving back and forth rapidly to capture the wide panorama of the ring system, and in the profound cold of space, its primary gear lubricant had failed, causing it to get stuck. For a terrifying 2 hours, the mission controllers on Earth were blind, their priceless explorer suddenly crippled just as it reached its destination. Working frantically, the engineers at JPL pieced together the clues. They diagnosed the problem as an issue of overuse and low temperature. They sent up new commands, instructing the spacecraft to move the platform much more slowly, to use its backup lubricants, and to avoid the rapid slewing that had caused the problem. It worked. The platform began to move again, sluggishly at first, but it was alive. The eyes of Voyager 2 were open once more. With its vision restored, Voyager 2 built upon its twin's discoveries, its different trajectory, allowing it to take even closer, higher resolution images of the rings and moons. It confirmed the bizarre nature of the spokes and the braided F ring, and it provided new perspectives on the icy moons. Then, its own tour complete, Voyager 2 faced its own moment of destiny. Unlike its sibling, its trajectory had been meticulously preserved. As it swung past Saturn, it performed its own perfect gravitational slingshot, a cosmic bank shot that used the planet's immense momentum to bend its path and accelerate it on a 4.5-year journey to its next target, the mysterious and distant ice giant, Uranus. The secret hope of the JPL engineers, the quiet gamble they had made years before when designing the spacecraft, had paid off. The grand tour was still on. As Saturn receded behind it, Voyager 2 set its course for an unknown world. A solitary pilgrim venturing ever deeper into the cold and the dark. The departure from Saturn marked the beginning of the loneliest and most challenging leg of the grand tour. For Voyager 2, the solar system ahead was a vast, uncharted sea. Its twin, Voyager 1, was now on a completely different path, climbing up and out of the plane of the planets, its voice receding into the cosmic static. Voyager 2 was now truly alone, a solitary pilgrim on a 4.5-year trek across nearly 5 billion kilometers, or about 3 billion miles, of barren, frozen space. The target was Uranus, a world so remote it was a complete enigma. Discovered by the British astronomer William Herschel in 1781, it was the first planet to be found using a telescope, a faint, greenish-blue dot that had languished in obscurity ever since. From Earth, it was a featureless disk, its secrets shrouded by immense distance. No spacecraft had ever visited this remote outpost, and the team at JPL knew they were venturing into a realm of almost total ignorance. This immense distance posed a new and profound set of technical challenges. As Voyager 2 sailed farther from the Sun, the twin enemies of distance and darkness grew more formidable. The radio signal, which had already been astoundingly faint from Saturn, was now stretched to the breaking point. By the time it reached Uranus, the probe's transmissions would be only a quarter as strong. To hear this infinitesimal whisper, humanity had to cup its ear to the cosmos more intently than ever before. The Deep Space Network, or DSN, NASA's global array of giant radio antennas in California, Spain, and Australia, underwent a critical series of upgrades. The dishes of the main antennas were enlarged. Their diameters increased from 64 to 70 meters, or from 210 to 230 feet, making them more sensitive. Furthermore, techniques were developed to electronically link multiple antennas together, a process called arraying, creating a single, more powerful virtual ear to listen for the probe's faint call. The communication time lag also became a significant factor. A command sent from Earth now took 2 hours and 45 minutes to reach the spacecraft, meaning a single round-trip conversation, a question and an answer, would take nearly 6 hours. The carefully programmed autonomy of the Voyager's computers was more critical than ever. The other great challenge was the ever-dwindling light. At Uranus's orbit, the Sun shines with only 1/400th of the intensity it has at Earth. It is less a life-giving star and more a brilliant, distant beacon in an ocean of blackness. This presented a severe problem for the cameras. To capture a clear image in such low light, the camera's shutter had to be left open for much longer, a technique known as long exposure photography. But Voyager 2 would be screaming past the planet and its moons at a velocity of over 60,000 kilometers per hour, or 40,000 miles per hour. A long exposure from a fast-moving platform would result in a hopelessly smeared and blurry image. To compensate, the engineers at JPL devised an ingenious technique called image motion compensation. They programmed the entire spacecraft to pivot with excruciating precision during the long exposures. As the camera shutter opened, tiny thrusters would fire in minute controlled bursts, rotating the entire 360-kilogram or 800-pound probe to track the target perfectly, keeping it locked in the camera's frame. It was like a photographer on a speeding train, smoothly panning their body to capture a crystal-clear image of a stationary object. It was an audacious and risky maneuver that had never been attempted before. As the years of silent flight passed, the mystery of Uranus loomed larger. The planet's most bizarre and defining characteristic was its extreme axial tilt. While Earth is tilted on its axis by about 23.5 degrees, giving us our seasons, Uranus has been knocked completely on its side, with an axial tilt of 98 degrees. It doesn't spin like a top as it orbits the sun. It rolls like a ball, with its poles alternately pointing directly at the sun for decades at a time. When Voyager 2 arrived in January of 1986, the planet's south pole was pointed almost directly at the approaching sun and spacecraft. A strange, bullseye configuration that no one had ever seen up close. This bizarre orientation raised a host of questions. What would this do to the planet's weather? Would one pole be perpetually hot, while the other was locked in a frozen, 42-year-long night? And what of its magnetic field? If it was generated by a molten core like Earth's, would it be aligned with the planet's rotation, creating a magnetic field that pointed out sideways into space? Scientists had theories, but no one truly knew what to expect. As Voyager 2 closed the final distance, the featureless, greenish-blue marble began to grow. But it refused to give up its secrets easily. The planet appeared almost completely bland, a placid, hazy ball of aquamarine, with none of the vibrant bands or swirling storms of Jupiter and Saturn. This calm exterior was a result of its extreme cold. The tops of its clouds were a frigid minus 214 degrees Celsius, or minus 353 degrees Fahrenheit. This cold temperature, combined with a thick atmospheric haze, masked the more dynamic weather churning deep within. Still, by painstakingly enhancing the faint contrast in the images, the science team was able to identify a few subtle, puffy clouds of methane ice. By tracking their movement, they were able to accurately measure the planet's rotation period for the first time, finding that a day on Uranus was a swift 17 hours and 14 minutes. The true surprises began when Voyager 2 passed through the invisible boundary of the planet's magnetosphere. The magnetic field it discovered was utterly bizarre, a magnetic monstrosity unlike anything previously encountered. It was not aligned with the planet's rotational axis. Instead, it was tilted by a shocking 60 degrees. Even stranger, the magnetic field was not centered in the middle of the planet, but was offset from the core by about a third of the planet's radius. The result was a wobbly, chaotic, and lopsided magnetic environment. As Uranus rotated on its side, its wildly tilted, off-center magnetic field tumbled and corkscrewed through space, a complex and dynamic structure that astonished the scientific community. As the probe continued its dive, it confirmed the existence of the 9 faint, narrow rings that had been discovered from Earth a few years earlier. But it also discovered 2 entirely new ones. Unlike Saturn's bright, broad rings of water ice, the rings of Uranus were as dark as charcoal, made of some unknown, carbon-rich material. They were thin and tenuous, like dark pencil lines drawn on the black canvas of space, and were held in place by the gravitational influence of newly discovered shepherd moons. And in its brief 6-hour dash through the heart of the system, Voyager 2 became an incredible moon hunter, discovering 10 new, small, dark satellites orbiting close to the planet, each one named, in keeping with tradition, after characters from the plays of William Shakespeare and Alexander Pope. But the most spectacular revelation of the entire encounter came from the most unlikely of sources. The smallest and innermost of Uranus's 5 previously known moons, a tiny ball of ice and rock named Miranda. Barely 470 kilometers, or 290 miles, in diameter, scientists had expected it to be a simple, uninteresting, crater-covered ice ball. Instead, the images that came back from Miranda were of a world that was a complete and utter geological freak. A body so bizarre it looked as if it had been built from a cosmic scrapbook of spare parts. Miranda's surface was a jumbled, chaotic patchwork of wildly different terrains, slammed together in a nonsensical fashion. There were old, heavily cratered plains, right next to young, smooth regions with very few craters. There were vast, grooved canyons that sliced through the landscape, some of them reaching depths of 20 kilometers or 12 miles, making them nearly 12 times deeper than Earth's Grand Canyon. Most strikingly, Miranda was home to 3 enormous rectangular or trapezoidal features called coronae. These were vast regions of parallel ridges and grooves, unlike anything seen anywhere else in the solar system. One, named Inverness corona, was a giant chevron-shaped feature that looked like a massive V carved into the moon's surface. Another, Arden corona, was a vast, racetrack-like pattern of concentric ovals. It was as if a geologist had been given pieces from 3 different puzzles and had tried to force them all together. The leading hypothesis to explain this spectacular mess was that Miranda had, at some point in its distant past, been the victim of a cataclysmic impact, a collision so violent that it shattered the moon into a collection of large, rocky, and icy fragments. Then, over time, the relentless pull of gravity slowly and imperfectly pulled these broken pieces back together, leaving behind the jumbled, chaotic, and breathtakingly beautiful mess that Voyager 2 witnessed. The flyby of Uranus was fleeting. After its brief, intense encounter, Voyager 2 was once again seized by the gravity of a giant planet. Its trajectory bent, its speed increased. The solitary traveler performed its final slingshot, perfectly positioning itself for the last leg of its historic journey, a 3.5-year coast to the final unexplored world on its itinerary, the distant blue giant, Neptune. The encounter with the strange, sideways planet and its fractured moon had been a resounding success, a triumph of engineering and a testament to human curiosity. The grand tour was entering its final, triumphant act. With the strange, sideways world of Uranus shrinking in its rearview mirrors, Voyager 2 embarked on the final and most remote chapter of its planetary saga. It was now sailing toward Neptune, the last of the gas giants, a world so distant and dim that it had been discovered not by a lucky glance through a telescope, but by the subtle, ghostly pull of its gravity on the orbit of Uranus. It was found through mathematics, a phantom planet predicted on paper before it was ever seen by a human eye. For 3.5 years, Voyager 2 crossed the immense, dark expanse separating the 2 ice giants. A final cruise through the profound cold at the very edge of the sun's planetary kingdom. The sense of anticipation at the Jet Propulsion Laboratory was mixed with a feeling of profound finality. This was it. This was the last stop on the grand tour. the culmination of a 12-year journey and 2 decades of work. There were no more gravity assists to be had, no more worlds to aim for. Neptune was the grand finale. The challenges that had tested the team at Uranus were now magnified to their absolute extreme. Voyager 2 was now nearly 4.5 billion kilometers, or almost 3 billion miles, from home. The light from the sun was 900 times weaker than at Earth, a pale, distant glow that offered little warmth and even less illumination. The radio signal stretched across this unimaginable void was now so weak that it was measured in quintillionths of a watt. To capture this faint, precious whisper, the Deep Space Network employed its full power, electronically linking the giant 70-meter antenna in California with the 27 antennas of the Very Large Array in New Mexico, creating a virtual radio telescope the size of a state to listen for Voyager's call. The time delay was now more than 4 hours each way. A command sent from Earth would not arrive until hours later, and the response would take another 4 hours to return. The mission was happening in a different time zone, one dictated by the speed of light itself. As the late summer of 1989 approached, the planet Neptune, a deep and mesmerizing azure blue, began to take shape on the monitors at JPL. Scientists had half expected another Uranus, a cold, quiet, and largely featureless ball of gas. Neptune was even colder than Uranus, despite being farther from the sun, a thermal mystery in itself. Logic suggested its atmosphere should be in a deep, frozen slumber. But the very first images to resolve detail showed that Neptune was anything but asleep. To everyone's astonishment, the planet was alive with weather. It was a dynamic, vibrant world, scarred by colossal storms and streaked with wispy, high-altitude clouds. The most dominant feature to emerge from the blue haze was a gargantuan, cyclonic storm, a churning, deep blue vortex that was immediately christened the Great Dark Spot. It was a storm of planetary proportions, roughly the size of the Earth. And in many ways, it was a mirror image of Jupiter's Great Red Spot, rotating counterclockwise and defined by powerful, shearing winds. Near it, a smaller, brighter, and more erratic storm zipped around the planet at a faster pace, earning the nickname Scooter from the observing scientists. Strewn across the upper atmosphere were bright, feathery clouds of frozen methane, delicate white streaks that resembled cirrus clouds on Earth, casting long, dark shadows on the deeper cloud decks below. This was a world of shocking meteorological violence. By tracking the movement of these clouds, the Voyager team measured the winds on Neptune and found them to be the fastest and most ferocious ever recorded in the solar system. Near the great dark spot, winds raged at speeds exceeding 2,400 kilometers per hour, which is close to 1,500 miles per hour. A supersonic tempest on a scale that dwarfed any hurricane on Earth. Voyager 2 also turned its gaze toward Neptune's faint and mysterious rings. Observations from Earth had suggested that Neptune might not have complete rings, but rather a series of disconnected arcs. The mystery was how such arcs could exist, as the laws of orbital mechanics dictated that the material should spread out evenly to form a full ring in a very short time. As Voyager flew past, it solved part of the mystery while deepening another. It found that Neptune did have several complete, dark, and tenuous rings, but the outermost one, named the Adam's ring, was indeed bizarrely clumpy. It contained 3 bright, dense arcs, which the team named Liberté, Égalité, and Fraternité. The particles in these arcs were somehow being held together, prevented from spreading out. The nearby moon, Galatea, was suspected of being the shepherd, its gravity creating a stable resonance that corralled the particles. But the precise mechanism remains a puzzle to this day. And in its final act as a moon discoverer, Voyager 2 spotted 6 new, small, dark moons orbiting close to the planet, their names drawn from the myths of the sea god Neptune. But the true climax of the Neptune encounter, the grand finale of Voyager's entire planetary tour, was the flyby of its largest moon, Triton. Triton was a world steeped in mystery. It was the only large moon in the solar system to orbit its planet in the wrong direction, a retrograde orbit that was a clear sign that Triton was not born with Neptune, but was a wanderer, an object captured from the distant Kuiper belt long ago. This cosmic abduction would have had catastrophic consequences, with tidal forces heating Triton's interior and likely destroying Neptune's original family of moons. As Voyager 2 adjusted its course for a close pass, just 40,000 kilometers, or 25,000 miles, above its surface, no one knew what to expect. What they saw was one of the most bizarre and spectacular worlds in the solar system. Triton was a stunning pinkish-white globe with a strange mottled surface and a thin, hazy atmosphere of nitrogen. Its surface temperature was the coldest ever measured on any object visited by a spacecraft, a staggering minus 235 degrees Celsius, a truly frigid minus 391 degrees Fahrenheit, so cold that nitrogen, the gas that makes up most of the air we breathe, was frozen solid into a transparent, rock-hard ice. The surface itself was a geological wonderland. One hemisphere was covered in a polar ice cap of frozen nitrogen and methane, tinged pink by the effect of solar radiation on the organic molecules. The other hemisphere was a bizarre, wrinkled landscape that looked for all the world like the skin of a cantaloupe, a terrain of dimples and ridges seen nowhere else. There were vast, smooth, frozen lakes, suggesting ancient volcanic plains where lava of slushy water and ammonia had once erupted and frozen over. The surface was young, with very few impact craters, a clear sign that the moon was, or had been, geologically active. But the most shocking discovery was yet to come. As the science team scanned the high-resolution images of the polar cap, they saw them. Dark, vertical streaks, all pointing in the same direction, like iron filings aligned with a magnetic field. They looked like stains on the ice. But when they compared images taken several hours apart, they realized with a jolt of disbelief that these were not stains. They were active plumes. They were geysers. From the frozen, sunlit surface of the coldest world ever visited, plumes of dark, sooty nitrogen gas and dust were erupting into the sky, rising to an altitude of 8 kilometers, or about 5 miles, before being sheared off by the thin upper atmosphere winds, creating the dark streaks that stretched for over 100 kilometers, or 60 miles. The team had discovered active cryovolcanism, ice volcanoes, erupting on a world that should have been frozen solid for billions of years. The likely mechanism was a kind of solid-state greenhouse effect, where the feeble sunlight penetrated the translucent top layer of nitrogen ice, warming a darker layer of material underneath. This trapped heat would cause the subsurface nitrogen to subluge, turning directly from a solid to a gas, building up pressure until it exploded through a vent in the surface, carrying dust and ice particles with it. It was a discovery of profound importance, proving that a world did not need internal heat from tidal forces, like Io, to be geologically active. Even in the deepest, coldest reaches of the solar system, the faint light of a distant sun could be enough to power a geological engine. The flyby of Triton was Voyager 2's final, triumphant performance. Its trajectory had been carefully designed to dive over Neptune's north pole and then down past Triton. This path used the gravity of the moon to make a final, sharp course correction, dropping the probe below the ecliptic plane and flinging it out of the solar system on a southward path, a mirror image to the northward departure of its twin. The grand tour was complete. In 12 years, 2 remarkable spacecraft had transformed our view of the solar system. They had turned distant points of light into living, breathing worlds of unimaginable beauty and complexity. The primary mission was over, but the journey was not. A new mission, the Voyager Interstellar mission, was about to begin, with the triumphant echoes of the Neptune encounter fading into the silence of deep space. The Voyager mission entered a new and profoundly different phase. The grand tour, the magnificent 12-year planetary ballet, was over. The two probes had fulfilled their primary objective with a perfection that exceeded the wildest dreams of their creators. They had fundamentally redrawn the map of our solar system, transforming it from a collection of 9 fuzzy points of light into a vibrant menagerie of complex, dynamic, and often bizarre worlds. Now, their trajectories were carrying them away from the sun, away from the family of planets, on a one-way journey into the abyss. There were no more destinations on the itinerary, no more worlds to photograph. A new mission began, one not of frantic, close-up discovery, but of quiet, patient exploration. The Voyager Interstellar mission. Its goal was to travel farther than any human object had ever gone, to find the true edge of our solar system, and to take the first tentative steps into the great ocean of interstellar space. Before the probes fell completely silent as visual observers, there was one final, poetic act to perform. The idea came from Carl Sagan, the visionary astronomer who had championed the golden record. He felt that before the mission turned its full attention to the long journey ahead, it was essential to perform a gesture of profound humility. He wanted to turn Voyager 1's cameras around one last time and take a final picture of home. From its new, lofty vantage point, high above the plane of the solar system, Voyager 1 could see all the planets it had passed and the one it had left behind as mere points of light. Sagan's request was not motivated by a desire for new scientific data. It was a plea driven by philosophy. He wanted to capture an image that would show humanity its true place in the cosmos, to see our world not as the center of everything, but as a fragile, lonely stage in a vast and indifferent arena. The idea was met with some resistance within NASA. Pointing the sensitive cameras back toward the inner solar system, so close to the bright, glaring sun, risked damaging their delicate optics. Furthermore, it required precious resources, computer time, antenna usage, and engineering effort for a photograph that held little to no scientific value. But Sagan was persistent, and his eloquent arguments eventually won over the mission planners. And so, on Valentine's Day in 1990, when Voyager 1 was a staggering 6 billion kilometers, or nearly 4 billion miles, from home, the commands were sent. The spacecraft, now a distant, silent servant, obediently swiveled its scan platform and for the last time opened the shutter of its camera. It took a series of 60 pictures, a mosaic of narrow-angle frames that captured the sun and 6 of its planets, a final family portrait of our solar system: Venus, Earth, Jupiter, Saturn, Uranus, and Neptune all appeared, each as a tiny, faint speck of light. Mercury was lost in the sun's glare, and Mars was too dim to be seen. Of all these images, one stood out, destined to become one of the most iconic and profound photographs ever taken. It was the picture of Earth. In the frame, our world appeared as a tiny, almost imperceptible point of light, a lonely pixel, less than 0.1% of the image's size, suspended in a scattered, coppery beam of sunlight. Sagan would later give it the name by which it would become famous: the pale blue dot. When the image was finally received and processed on Earth, its power was undeniable. It was a picture of almost nothing, yet it contained everything. Sagan, in his book of the same name, would later immortalize the image with words that captured its deep and humbling significance. He urged us to look again at that dot. "That's here," he wrote. "That's home. That's us." He described how on that tiny, distant speck, everyone you love, everyone you know, everyone you have ever heard of, every human being who ever was, lived out their lives. It was the aggregate of our joy and suffering, of thousands of confident religions, ideologies, and economic doctrines. It was the stage for every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, every hopeful child, every inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. The photograph was a silent, powerful rebuke to our delusions of self-importance, a sobering perspective on our own quarrels and our place in the universe. It showed our world as a fragile, precious, and irreplaceable home that we must cherish and preserve. Shortly after taking this final, poignant photograph, a final command was sent to Voyager 1. Its cameras were powered down forever. The same was done for Voyager 2. Their eyesight, which had shown us the wonders of the outer planets, was sacrificed. The precious, dwindling power from their nuclear generators was needed for the long, dark road ahead, to keep alive the instruments that could feel the invisible particles and fields that would be their only companions on their journey to the stars. The probes were now blind pilgrims, their mission transformed from one of sight to one of touch and hearing, sensing the very fabric of space itself. Their new destination was a place, not a planet. It was the heliopause, the theoretical, invisible boundary that marks the edge of the sun's influence. Our solar system is not just a collection of planets floating in empty space. The sun is an active star, and it constantly breathes out a powerful stream of charged particles, protons and electrons, known as the solar wind. This wind travels outwards in all directions at supersonic speeds, creating a vast magnetic bubble around the solar system called the heliosphere. This heliosphere is our home, our cosmic cocoon. It extends far beyond the outermost planets, shielding us from the harsh, high-energy cosmic rays that originate from distant supernovae and other violent celestial events. The space outside this bubble, the thin, cold gore and dust that fills the vast gulfs between the stars, is known as the interstellar medium. The Voyager interstellar mission's objective was to cross the boundary where the sun's bubble meets this interstellar medium. This boundary is not a simple, single line, but a series of complex, layered frontiers. The first of these is the termination shock. This is the point where the solar wind, after traveling unimpeded for billions of kilometers and miles, abruptly slows down from supersonic to subsonic speed as it begins to press against the inward pressure of the interstellar gas. It is a shock wave, a cosmic version of the sonic boom created by a supersonic jet. Beyond this lies a turbulent, frothy region known as the Helios Heath, a kind of cosmic no man's land where the slowed-down solar wind is churned and mixed as it's deflected by the interstellar medium. And finally, at the very edge, is the heliopause, the cosmic shoreline, the final, definitive border where the pressure of the solar wind and the interstellar medium reach equilibrium. This is the point where the sun's breath finally gives way to the interstellar breeze. Crossing it would mean leaving the solar system for good. For more than a decade after the Neptune encounter, the probes sailed on, silently and patiently, through the vast, dark emptiness of the outer heliosphere. The mission team on Earth grew older, some retiring, others passing away. A new generation of scientists taking their place to listen to the faint, steady heartbeat of the aging explorers. The power from the RTGs continued its slow, inexorable decay, forcing the engineers to make difficult, painful choices. to conserve energy, instruments were turned off, one by one, a slow, calculated process of saying goodbye to the spacecraft's senses, ensuring that the most critical instruments for detecting the interstellar boundary would remain alive for as long as possible. Voyager 1, being faster and on a more direct course, was the scout, the first to approach this invisible frontier. In late 2004, at a distance of nearly 14 billion kilometers, or about 8.5 billion miles, from the Sun, its instruments detected the telltale signs that it had finally reached the termination shock. The speed of the solar wind particles it was measuring suddenly and dramatically dropped. It had crossed the first boundary. It was now in the turbulent, unpredictable waters of the Helios Heath. It had entered the beginning of the end of the solar system. The spacecraft, a silent emissary from a pale blue dot, was now on the cusp of its greatest and most profound discovery: the crossing into the sea of stars. Having crossed the first great boundary of the termination shock, Voyager 1 found itself in a strange and turbulent new reality. This was the Helios Heath, a vast, chaotic region that scientists had imagined but never before experienced. It was a kind of cosmic purgatory, a final, stormy frontier separating the familiar realm of the Sun from the great unknown of interstellar space. Here, the solar wind, having slammed into the wall of interstellar pressure, was no longer a smooth, supersonic flow. It was now a hot, dense, and turbulent mess, a cosmic froth where the Sun's influence was churned and deflected. For 8 long years, Voyager 1 battled its way through this tumultuous sea. Its instruments, designed to measure particles and magnetic fields, painted a picture of a region far more complex and far larger than anyone had predicted. It was as if the probe, having crossed the smooth, open ocean, had suddenly found itself in a chaotic surf zone, buffeted by unpredictable currents and swirling, magnetic eddies. Back on Earth, a new generation of scientists, many of whom were children when the Voyagers were launched, watched their data with a mixture of excitement and puzzlement. They were waiting for the final signal, the definitive proof that the probe had punched through the last layer of the Sun's cocoon and reached the heliopause. They knew what they were looking for: the solar wind particles, which had dominated the probe's environment for its entire 35-year journey, should suddenly vanish, their numbers plummeting to near zero. Simultaneously, the probe should be inundated by a flood of high-energy galactic cosmic rays, particles from distant supernovae that the heliosphere had always shielded it from. The magnetic field should also change, shifting its direction and intensity as the probe passed from a field generated by our Sun to one shaped by the entire galaxy. Several times, the data seemed to show that the moment had arrived. The probe would detect a sudden drop in solar particles and a surge in cosmic rays, and an excited buzz would ripple through the mission control team. But just as they thought the crossing was imminent, the readings would revert. The solar wind would return, and the cosmic ray count would drop again. It was as if Voyager 1 was dipping its toes into the interstellar ocean, only to be pulled back by a retreating wave. The boundary was not a clean, simple line, but a porous, dynamic, and fluctuating frontier. For a time, the probe seemed to be traveling along what scientists called a magnetic highway, a region where the Sun's magnetic field lines were connecting directly with the interstellar field lines, creating temporary portals that allowed particles from both sides to mix. The probe was tasting the outside, getting tantalizing hints of the space beyond, but it had not yet truly left home. Then, in the summer of 2012, the data changed, and this time, it did not change back. On August 25th, at a distance of more than 18 billion kilometers, or 11 billion miles, from the Sun, the instruments aboard Voyager 1 recorded a sudden, sharp, and permanent drop in the number of solar wind particles. They didn't just dwindle, they vanished, their levels falling by a factor of 1,000. At the exact same moment, the intensity of the galactic cosmic rays spiked dramatically, reaching the highest levels ever recorded. 2 of the 3 key signs were now unequivocally present. The only piece of the puzzle still missing was a change in the magnetic field. Its intensity increased, but its direction did not shift as predicted. This caused a heated debate within the scientific community. Had it truly crossed? Or was it in some final, bizarre, and unknown layer of the solar system? The definitive proof came months later, not from a direct measurement, but from a lucky cosmic coincidence. In the spring of 2013, the Sun unleashed a powerful coronal mass ejection, a wave of plasma that raced outwards through the solar system. The science team waited patiently. They knew that when this wave eventually reached the heliopause, it would strike the interstellar plasma and cause it to vibrate, to ring like a bell. In April, nearly a year after the wave had left the Sun, Voyager's plasma wave subsystem instrument heard that ring. It detected the telltale vibrations of the surrounding plasma. By analyzing the frequency of these vibrations, the science team could calculate the density of the plasma the probe was flying through. The number they got was astounding. The plasma was 80 times denser than anything the probe had encountered in the Helios heath. It was the dense, cold plasma of the interstellar medium. The evidence was now undeniable. Looking back at their data, they realized the crossing had indeed occurred on that fateful day in August 2012. Voyager 1 had slipped the bonds of its home star and was now, officially and forever, an interstellar traveler. It was the first object made by human hands to enter the sea of stars. It was a moment of quiet, profound triumph. There were no cheering crowds or ticker tape parades, only the silent satisfaction of a team of scientists who had followed a faint, distant whisper to the edge of the known world and beyond. The probe was now flying through the breath of the galaxy itself, the thin, ethereal medium of gas and dust from which stars and planets are born. It was directly sampling the material from which we all came. Meanwhile, its twin, Voyager 2, was continuing its own long journey. Following a different, more southerly path, it was exploring a different part of the Helios heath, providing a crucial second data point. The heliosphere is not a perfect sphere. It's a dynamic structure with a blunt nose on one side and a long, comet-like tail on the other, shaped by its motion through the galaxy. Voyager 2's crossing would give a more complete picture of this complex boundary. And in November of 2018, at a distance of about 17 billion kilometers, or 10.5 billion miles, it too made the leap. Its crossing was cleaner and more definitive than its twins. The instruments detected the sharp drop in solar particles, the dramatic spike in cosmic rays, and this time, the expected shift in the magnetic field all at once. The dream had been fulfilled twice over. Humanity now had two ambassadors plying the interstellar seas. Today, the two Voyagers continue their oilant, lonely journey, their voices growing ever fainter, their power slowly ebbing away. They are now fantastically distant. Voyager 1 is over 24 billion kilometers, or 15 billion miles, from Earth, a distance so vast that its radio signal, traveling at the speed of light, takes more than 22 hours to reach us. Their power comes from the slow, steady decay of their plutonium generators, which have now been running for nearly half a century. Each year, their power budget shrinks by about 4 watts. To keep the probes alive, to eke out every last precious moment of data, the engineers on Earth have been forced to become masters of conservation. Over the years, they have sent commands to shut down non-essential systems, one by one. The cameras were first, followed by heaters for various instruments. It is a slow, poignant process of saying goodbye, a managed, graceful decline. In a remarkable testament to their 1970s era construction, many of the instruments have continued to operate perfectly, even after their survival heaters were turned off, surviving in temperatures far colder than anything their designers had ever dared to test them for. Their mission now is simply to fly on, to report on the conditions of interstellar space for as long as their faint electronic heartbeats can be sustained. It is expected that by some time around 2025, or shortly thereafter, there will no longer be enough power to run even a single scientific instrument. One by one, their senses will be extinguished. And then, sometime in the 2030s, they will fall completely silent. The faint carrier signal that has been their lifeline to Earth for over 50 years will cease, and the giant antennas of the deep space network will hear only the background hiss of the cosmos. Their scientific mission will be over, but their ultimate journey, their final mission, will have only just begun. They will become silent, drifting artifacts, ghosts of humanity sailing on the gravitational currents of the Milky Way. For tens of thousands of years, they will travel in the dark. In about 40,000 years, Voyager 1 will pass within about 1.5 light years of a small, dim star in the constellation Camelopardalis called Gliese 445. In about 300,000 years, Voyager 2 will pass about 4 light years from Sirius, the brightest star in our night sky. They are time capsules, carrying with them their golden records, their gentle greeting to the cosmos. They are humanity's farthest and most enduring legacy, a testament not to our power or our glory, but to our curiosity, our hope, and our innate, unquenchable desire to reach out, to explore, and to understand our place in the silent, star-strewn darkness. The story of the Voyager program is, in the end, a story about time. It is a tale measured not just in the hours and days of a mission, but in the decades of a human lifetime and the unfathomable eon of cosmic drift. The legacy of these two remarkable spacecraft is a testament to what humanity can achieve when it aims for the timeless, when it builds not for the next budget cycle, but for the next millennium. Voyager 1 and Voyager 2 are now far more than just aging pieces of robotic hardware. They are cultural touchstones, technological artifacts that have transcended their original purpose to become enduring symbols of our species' highest aspirations. Their journey has carved a permanent mark not only on the physical space of our solar system, but on the intellectual and emotional landscape of our civilization. The scientific legacy of the Voyager program is, by any measure, staggering. Before the twin probes set sail, the outer planets were little more than faint, fuzzy disks in our most powerful telescopes, their moons mere points of light. They were worlds of speculation and theory. Voyager transformed them into real places. The mission was a torrent of discovery, a complete and total rewriting of the textbooks. It gave us our first close-up view of the violent, churning atmosphere of Jupiter and its colossal, centuries-old storm. It revealed the fiery, volcanic heart of Io, a world constantly remaking itself under the immense gravitational strain of its parent planet. And it unveiled the tantalizing possibility of a hidden, life-bearing ocean beneath the icy shell of Europa. At Saturn, it dissolved the placid, solid-looking rings into a shimmering, intricate tapestry of thousands of ringlets, a dynamic system of braids, spokes, and shepherd moons that behaved in ways that seemed to defy the known laws of physics. Then, the mission pressed on into true terra incognita. It gave us our first, and to this day, our only, close-up encounter with the ice giants. Voyager 2 revealed the strange, sideways world of Uranus, with its bizarre, tumbling magnetic field and its fractured, Frankenstein's monster of a moon, Miranda. And as a grand finale to the planetary tour, it showed us the stunning, azure blue beauty of Neptune, a world racked by the fastest, most supersonic winds in the solar system. It discovered active geysers of nitrogen erupting from the frozen surface of Triton, proving that even in the deepest, coldest reaches of the solar system, there can be geological activity. These were not just incremental advances in knowledge. They were revolutions in planetary science. Every flyby produced a cascade of discoveries that overturned old theories and posed a dozen new questions for everyone it answered. The Voyager data became the foundation upon which entire careers were built, and it continues to be a vital resource for scientists today, a priceless archive of a moment in time that will never be repeated. The mission was the definitive reconnaissance of the outer solar system, a foundational survey that paved the way for every subsequent mission, from Galileo and Juno at Jupiter to Cassini at Saturn. Beyond the raw scientific data, the Voyagers left an indelible mark on our culture. The images they sent back were more than just scientific artifacts. They were works of art, cosmic masterpieces that revealed a universe far more beautiful, strange, and magnificent than we had ever imagined. These pictures entered the public consciousness, adorning the covers of magazines, appearing in films and television shows, and inspiring a generation of future scientists, engineers, artists, and dreamers. The image of the great red spot, the intricate dance of Saturn's rings, and most profoundly, the distant, humbling view of the pale blue dot became icons of the space age. They gave us a new perspective on our home, framing it not as a vast, limitless expanse, but as a fragile, precious, and lonely outpost in a vast cosmic ocean. The mission provided a sense of shared adventure for all of humanity. In an era often marked by division and conflict on Earth, the Voyager story was one of pure exploration, a tale of human curiosity reaching out to the unknown on behalf of the entire species. The technological legacy of the Voyager program is equally profound. These spacecraft were built in the 1970s with computers that had less processing power than a modern car key fob. Yet, they were designed and built with such incredible robustness and foresight that they have lasted for nearly half a century, enduring the harsh radiation of Jupiter's magnetosphere, the profound cold of deep space, and the simple, relentless decay of time. The mission was a masterclass in long-duration spaceflight. The use of gravity assists, the design of radiation-hardened electronics, the creation of fault-tolerant, autonomous software, and the development of incredibly sensitive communication systems all pushed the boundaries of what was possible. The solutions that the JPL engineers devised to overcome the immense challenges of distance, darkness, and time became standard practice for subsequent interplanetary missions. The incredible longevity of the probes is a testament to the skill and dedication of the people who built them, a quiet monument to human ingenuity. And then there is their final, and perhaps their most enduring, legacy. As the Voyagers continue their silent, endless journey into the interstellar void, they carry with them the golden records, a single, hopeful gesture cast into the cosmic ocean. The chances of this message in a bottle ever being found by an extraterrestrial intelligence are infinitesimally small. The probes will drift for hundreds of thousands of years before they even come remotely close to another star. And by then, they will be cold, dead, and silent artifacts. But the true significance of the golden record was never really about making contact. It was about us. The act of creating the record was a profound exercise in self-reflection. It forced a small group of people to step outside of their own time and culture and ask a fundamental question. What is the best of us? What is worth preserving? The music of Bach and Chuck Berry, the sounds of a human heartbeat and a crashing wave, the images of our art, our science, and our diversity. This was the story we chose to tell about ourselves. The golden record is a symbol of our better angels, a testament to a species that, for all its flaws and failings, is capable of looking up at the stars and offering a message of peace, beauty, and hope. The Voyager saga is a complete story, with a beginning, a middle, and an end. It began with a rare celestial alignment and a dream of a grand tour. Its middle was a spectacular 12-year crescendo of discovery that forever changed our view of our own cosmic backyard. And its end is a long, slow, graceful decline into silence. A final, poignant chapter that sees the probes becoming humanity's first true emissaries to the stars. They are now fulfilling their final mission: to drift for eons through the Milky Way as silent ambassadors from a small blue world that once dared to reach out. Their journey is a reminder that we are a species of explorers, driven by an insatiable curiosity that pushes us to see what lies over the next hill, across the next ocean, and beyond the next planet. The story of Voyager is our story, a timeless epic of human ingenuity and our unquenchable desire to understand our place in the silent, star-strewn darkness. And so, our grand tour of the cosmos comes to a close. We have traveled with two of the most remarkable machines ever built, from their conception in the minds of a few far-sighted dreamers to their lonely, silent trek through the sea of stars. We began with a fleeting celestial alignment, a once-in-a-lifetime opportunity to visit the giant outer worlds. And we followed as Voyager 1 and Voyager 2 fulfilled that dream with breathtaking perfection. They were our eyes and our senses, transforming the faint, distant points of light we knew as Jupiter, Saturn, Uranus, and Neptune into vibrant, living worlds. They showed us the fiery volcanic heart of Io and the icy promise of a hidden ocean on Europa. They revealed the baffling, beautiful complexity of Saturn's rings and the thick prebiotic haze of Titan. They gave us our only close-up view of the strange, sideways mystery of Uranus and its shattered moon, Miranda. And as a grand finale, they unveiled the supersonic winds of Neptune and the impossible nitrogen geysers of Triton. But the Voyagers did more than just rewrite our scientific textbooks. They changed our perspective. By turning their cameras around for one last look home, they gave us the pale blue dot, a single, humbling photograph that captured our world as a fragile, lonely mote of dust suspended in a sunbeam, a powerful reminder of our shared place in the universe. Now, their planetary mission is a distant memory. They are humanity's first interstellar emissaries, having crossed the invisible shoreline of the heliopause to sail on the cosmic ocean. Their power is fading, and their voices are growing ever fainter. But their ultimate journey continues. Drifting silently for eons to come, they carry with them a golden record, a hopeful greeting from the species that built them. The Voyager saga is a testament to the power of human curiosity, a story of what we can achieve when we dare to aim for the timeless. The two probes are our farthest and most enduring legacy. A quiet whisper sent into the great unknown, carrying a message of who we were, what we learned, and our unending desire to reach for the stars.